Okay, great. So, we're ready to see another really interesting property of quantum computing, quantum physics, which is, this very famous no cloning theorem. So, this is a really fantastic thing. So, this what the no cloning theorem says, okay, what is written here is formal. Okay, since everyone is staring at it, I'll read it out. So, there does not exist any unitary transformation U such that for any state psi, I can copy psi. Okay, so basically U of psi tensor 0 gives me psi tensor psi. Why do I have this extra 0 here? I mean, why do I not just write U of psi is psi comma psi? It's just because unitary transformation is square. So, you can think of it just as an empty register, this 0 over here, right. So, when I create something, I mean I am copying, right, I am not giving birth to a new state. So, if I am copying, I need to copy it to some place. So, you can think of this register as that, yeah. So, this is what the weakened no cloning theorem is. So, the sort of the full no cloning theorem also requires you to talk about measurements, which we will not do. We are just saying that within the quantum state, right, within the quantum system, we will not be able to copy. We are saying that, right. We are not talking about like the whole thing. Finally, you want to be able to say that at the end of the process, you should not end up with a copy of the state you started with. We won't do all that, but this is already very cool, right. So, first of all, I mean, this is really fundamentally different from what we are used to with classical computers, isn't it? And actually, a lot of the work that we do in cryptography is to prevent things like copying, right, also as teachers. But basically the idea is that in digital information you can obviously always make copies, as many copies as you want, and this is often a problem, right, from a security perspective, from a privacy perspective. I had already given you one example in the very first class, right, like with digital currency. So, if I have a certain Bitcoin, for instance, as my currency, now what is going to guarantee that I somehow don't make many copies of this Bitcoin and keep using it again and again? It's finally just a string, right. And typically we use some high end cryptography to mitigate these kind of problems. Right. Another example is that let us say that we're in this organization and everybody has a secret key, and now one of you leaves, okay, one of us leaves. Now at the time that the person leaves, we want to revoke their secret key, because they should no longer be able to read the privileged communication that is there in the organization. How will you ever revoke? This is a big problem, right? I mean, you have the key. I have no way of ensuring that you have deleted this key. You could have made any number of copies of it. Maybe you came up with some complicated function such that that function applied to a random string results in this key, and now you are storing it. My point is, you can hide this in any number of ways, right? You could just remember it, memorize it. There is no way one can get to that. Of course, present day passwords make that almost an impossibility, but still. So, what the no cloning theorem tells you is that actually with quantum states you cannot do this copying, at least not so easily. So, what do I mean by not so easily? I mean that a classical bit is still a quantum state, right? So, in that sense, of course, I can still copy classical things, right, but for an arbitrary state psi, I cannot have a sort of universal method of copying it. That is what this theorem is saying. So, this is sort of really exciting, and we'll see that it leads to some really cool cryptographic constructions. So as I've already said before, you know, in the second half of the course, we'll try to like deal with the problems that are problems and opportunities that are created by quantum computing for cryptography. Okay, so we will break a lot of present day cryptography, but we will also give rise to new and exciting possibilities, and using this no cloning property to get things like quantum money, for instance, is one of the things that I hope we will see later in this course. Okay, so let me do a proof of this weekend no cloning. There are many ways of proving it. I will choose a very simple one. So, I will start with a contradiction, right. So, suppose that, not a contradiction, I mean I will show the contrapositive. So, suppose that that does exist. Exists such a U. Then what can I write? Well, you know, U tensor 0, U of 0 tensor 0 should give me what? 0 0, right. Similarly, U of 1 tensor 0, this should give me 1 1, yeah, just by definition. And this implies by linearity that U of 0 plus 1 over root 2 tensor 0 is this. Everyone agrees? But now we have a problem, because if I consider the LHS, okay, then U of plus tensor 0 by definition should be what? It should be plus tensor plus, right? Right? And it is very easy to check that this and this are not equal. So, plus is, of course, it is basically right, this is this, and this is not equal to 0 0 plus 1 1 over root 2. So, we got a contradiction. So, the question was that you know, we did not use the fact that U is a unitary anywhere in this, and that is true that we did not explicitly invoke the fact that U is unitary, but as he points out, basically it is implicitly there, because otherwise I cannot even write, I mean I cannot even write, for example, this equation, right. I cannot say that I got a valid qubit in the end if U were not unitary. So, it is being implicitly used. So, that is a very good observation. Okay, so as I already said, couple of things to note is that we did not deal with measurements. So, this is not the full no cloning, and the other thing to note is that you know, this extra 0 state here is there because U is square, and think of it as a register in which we will copy the new state. Are there any questions? So, let us talk a little more about you know, no cloning. So, as I already alluded to, basically is it a blessing or a curse? I mean, from the cryptography or from the security point of view, there are certainly many cases where it can be a blessing, because in the classical setting the fact that you can copy easily really does create a lot of problems. For instance, the most simple idea in cryptography is this eavesdropper on a channel, right? In fact, I remember the first class when I asked you all what do you understand by cryptography, almost everybody was thinking of the sender and receiver trying to communicate privately, right? That's very old fashioned, by the way, but it's the most common thing we would do in cryptography. And now how does something like no cloning help? If you have an eavesdropper on the channel, then this eavesdropper cannot eavesdrop without altering the state. This is the idea, right? So it's not that it can listen in and make a copy and send it along again. Okay, so this is not, I am not saying anything formal at the moment. Just a discussion on what the possible implications of no cloning might be. Another one which I already talked about was digital money, right? So we will see in this class hopefully the notion of quantum money. So okay, another very good question. So the question is that maybe you can clone things based on what you have, like maybe there is no universal way, but maybe you can clone based on what you have. So once again I would like to hear from the rest of you, what do you think? Is that a problem? I mean, first of all, can we do it? Secondly, if we can do it, is that a problem? Okay, so yeah, sure. I mean, what he said is that if we know it is classical, then of course we can clone it. Yeah, so I already said that, I mean, classical is also quantum, right? So of course you can clone classical stuff. In response to the larger question that he asked, which is that maybe you can have sort of special transformations for different things. I have a couple of answers to give. So one of them is that you do not know, right, what state you have. Unless you perform a measurement, you get no information about it, right? So that is one thing that, I mean, in some sense, if I don't know what's in the box, right, then how will I choose a transformation based on what's in the box? So there is a circularity there. The other thing is that if I do know, right, then it's no longer cloning. I can prepare the state on my own. I didn't understand the question properly. Let me repeat the question. Does this mean we cannot build a cloning transform using partial measurements? So yeah, I mean, I think what you're getting at is that maybe I can learn some partial information by doing a partial measurement, but there is no very concrete question in what you are saying, but my answer would still be that whatever you learn, in some sense basically there is something that you don't know and something that you know. I mean, whatever it is that you know, using that you could always reproduce a state that is faithful to whatever you learnt, right? What is being said is that for example, in the entangled situation, right, you were saying that if I do a partial measurement, now I know the second one. So you said that therefore in some sense I copied it. I want to say that this is not copying by any definition of copying. No, not only that, not only is it the fact that it stops being a quantum state after you measure it. I want to say that the fact that the measurement causes the state to collapse, right, and it tells you what the other qubit is going to be. I will not call this copying. So one has to have a formal idea of what copying means, and I want to say that this is what we mean by copying. Fine, you don't have to use a universal U. If we proved this theorem for a universal U, let's forget about the universal U, but whatever transform it is, right, so some transform T, what it means for copying is that it takes whichever state you want, right, and it takes, let us say, 0, and it makes a copy. So now in the setting of entanglement, if I measure one qubit and this tells me what the other qubit is going to be, this is, I would not call this copying. Does that answer the questions? Yeah, great discussion. So, good. So, yeah, so these are the things around no cloning and these different properties that we have, which we are going to try to understand better and try to use in all the rest of the course. Okay, so far what we did is, we saw how to represent quantum information, both single and multi bits. We saw how to measure a quantum system, both single and multi bits, right. So, in the case of multi bits, we talked about partial measurements. We saw how to compute on a single qubit. How is that? By unitary transformations. So, now what about computing on multiple qubits? So, that is an obvious next question, and even classical computers can compute on multiple bits, right. So, at the very least, and classical computers can do sort of very fancy circuits, right. So, your phone has a circuit in it, there are circuits in the elevator, there is a circuit. So, you want to at least be able to do your regular classical circuits and more. Okay, so how shall we do that? That is what we want to talk about next. So, let us start with a few simple multi-bit operations, and then where I am going with this is that I would like to show you that we can do all of classical computation, and how I will do that is by emulating the NAND gate. Okay, so for those of you who are not from computer science, the NAND gate is the not AND gate, right. Everyone knows the AND gate, okay, and the NAND gate is universal for classical computation. What this means is that any circuit which has AND, OR and NOT gates, I can rewrite that circuit just using NAND gates, and there are simple ways in which one can show this. So, since we have a large audience not from CS, I will show a simple argument why this is the case. Okay, and then having seen that, what we'll show is that there is a quantum gate that simulates this NAND gate. So, therefore, all of deterministic computation in the classical setting will get captured by that. Okay, this is where we will head first, and then of course, we will go to the more exciting aspect, which is how to do more. Okay, so let's first at least establish that we didn't lose anything by moving to quantum. Okay, so let's look at a few simple gates as usual to begin with. So, this gate, the sort of the control NOT gate. So, this is a gate which may seem a little bit pointless at first, but turns out to be very useful. So, this is just like the NOT gate, but it lets you control when the NOT is applied. So, it does not always flip the bit. What it does is it flips the bit when the control bit is 1. So, here our X here is the control bit. Okay, so we can stare at this input and output. Okay, so this is my input, this is my output. So, first of all, you can see that when the control bit is 0, the output is unchanged, right. And when the control bit is 1, the output is, oh wait, what is going on? Oh yeah, I am just reading it wrong. Yeah, this is correct. So, when the control bit is 1, the output is flipped. And yeah, I mean that is all there is to it. This is the C NOT gate. Any questions about this? Okay. So, good. So, let us look at a quick example. So, what is C naught of this state over here? So, first I want to say that this is just the ones where the control bit is 0, right. So, here the control bit is 0. So, the second bit, the data bit does not get flipped, and where the control bit is 1, it is going to get flipped, right. So, this will become 1 1 plus 1 0. Okay, so this is what you will get, and you can once again write it as a matrix as shown here. So let's write down this matrix. Right. So you can see now, if I apply this matrix to this state, then only these two will get flipped. This will be alpha 0 0, this will be alpha 0 1, this will be alpha 1 1 and alpha 1 0. Okay. So you just flipped the last two. Yeah, so nothing deep going on. It's just a useful gate, controlled NOT. Now here is one of the star gates. So this is the Toffoli gate. It is the controlled NOT gate. So I mean, there's a lot of controlling in the name. It's a very useful gate, and sort of quick spoiler is that this is our universal NAND gate. Even though frankly, when you see it for the first time, that's a little hard to believe, because what it's doing is something which seems somewhat not, at least not very useful, if not completely useless. What it's doing is it flips the target if both control bits are set to 1. Let's look at this truth table. Okay, so by the way, I mean, these gates are very important, so let's pay close attention to them. So this is our Toffoli gate. Okay, what is it doing? So let's look first on the leftmost side. So A goes to A, right? B goes to B. Then I have A and B. I'm taking the AND. So this is the AND gate. Okay. And then I am taking the XOR with C, and this is what I output over here. Okay. So if A, B is 1, which means that both A and B are 1, right? In that case, C gets flipped. Yeah. Okay. And the truth table is written over here, right? So it does nothing here, do nothing, because there are only two entries which have both control bits as 1, and that is where you flip target. Also the matrix looks like this. So everything, it's basically identity except for the last two rows and columns, and there you get this flip over here as you see here. So yeah, it needs to flip. So these are the control bits, right, and this is the target. So you should flip the target. Good, thanks for pointing that out. Don't want to create confusion. Okay, so our claim is that Toffoli is an implementation of the AND gate, and yeah, so here it is correct. Okay, so this is 1, this is 0. So why is it an implementation of the AND gate? How will I use this gate to simulate AND? So what he said is that, well, only both the targets are 1, it is doing something. So therefore it is an implementation of AND, because if my C is always 0, then C XOR 0 is 0, I mean 0 XOR 0 is 0 and 0 XOR 1 is 1. So if I set C equal to 0, then I get the AND gate. Very good, that was the answer I was looking for. And now what about NAND? C equal to 1, right? So C equal to 1 gives me the NAND gate. Okay. Now so another thing that the CC0 or Toffoli gate allows me to do is simulate fan out. Okay, so let's recall the definition of fan in and fan out. In a general circuit, the number of wires that are going into a gate is called fan in, and the number of wires that come out are called fan out, just that. Okay. So, basically here you can see that I have some value coming out. Of course, this is classical terminology, right. So, we have to see what it means in the quantum setting, but in the classical setting I have a wire, I could attach 5 more wires and transmit the same bit, that is the idea. And in normal general circuits we do that. Okay. So, our claim here is that the Toffoli gate can be used to simulate fan out, and I claim that this lets you do it. So, if I set the first wire to 1 and the last wire to 0, right, then remember I had C XOR AB, right. So, because they call this A, I will call that B, right. So, so this is nothing but AB when C is 0, right, and if my B is always 1, then this is just A. So, what is this doing? This is taking an A and it is creating 2 A's. So, why is this not a contradiction to the no cloning theorem? Let us end the class on this note.